After discussing the theorem of parallel axis, in this video we will try to understand the theorem of perpendicular axis. As in the previous video, I have put up here over here the statement of the theorem just to save time. And again, like in the previous video, before we get into the statement, I'll try to give you a background about the theorem of perpendicular axis. So what this theorem says is that, let us say we have a plane lamina, right? So let us say we have a plane lamina like this, and let us say we have an axis perpendicular to this plane lamina. So let us say we have an axis perpendicular to this plane lamina, and we'll call this axis ZZ dash or axis ZZ. Right? The theorem says that the moment of inertia of this plane lamina about this axis, which we will denote by IZZ, right, is equal to IXX plus IYY, where XX and YY are two axes which are perpendicular to each other and are in the plane of this lamina. So let us say this is axis Y, right? And this is axis X. Right? So these two axes XX and YY, so you can show it over here, X, and I can extend this in this direction and say Y. Right? These are two axes which are in the plane of the lamina. Right? Z is perpendicular to the lamina. These two are in the plane of the lamina, and they are such that they pass through this particular point, which is in the plane of the lamina and passing through the Z-axis. So what the statement of the theorem of perpendicular axis says is that the moment of inertia of a uniform plane lamina about an axis perpendicular to its plane is equal to the sum of the moment of inertia about any two mutually perpendicular axes. Any two mutually perpendicular axes in the plane. These two axes have to be in the plane, intersecting on the first axis, and they should intersect on the first axis. So I can't have these two axes over here, they're intersecting over here. They have to intersect on the first axis, the perpendicular axis, and also they should be in the plane of the lamina. So IZZ is equal to IXX YY, where XS and YY are two axes which meet these conditions, that is, they are in plane of the lamina and intersected. Okay, so now let us look at the how did we get this theorem of perpendicular axis, right? And the proof is very, very simple actually. So let us say we have a point P in the lamina, right? Let us say we have a point P in the lamina, right, over here, which is of mass m, right? Then the moment of inertia of, right over here, moment of inertia of point P about the ZZ axis will be given by mr square, where let us show the distance r over here, right? Let us say this distance is r, this is point P, this distance is r, right? Will be mr square, mass into the distance from the x-axis. Now similarly, IZZ for all the points would turn out to be sigma mr square, right? So the moment of inertia of this plane lamina about ZZ axis is sigma mr square, where m is the mass of each and every particle and r is the respective distances from the ZZ axis, sigma r square. Now if you look at this particular and do a little bit of geometry over here, and if I try to complete this, so this particular point P is at, let us say, distance from the x-axis is x, and this distance from the y-axis is y. Okay? So if this is x, this also will be x. If this is y, this distance will also be y. Okay? Now this angle is 90 degrees. Therefore, if I look at this particular triangle, right, this is, let us say, OP, and let us call this T. Right? So in triangle OPT, what do I get? R is the hypotenuse, so I'll get r square is equal to x square plus y square. R square is equal to x square plus y square. Therefore, if I go back to this, IZZ is equal to sigma m, r square is x square plus y square, which can be written as sigma m x square plus sigma m y square. And x is the distance from the x-axis. So this will give me moment of inertia about the x-axis. This will give me the moment of inertia about the x-axis. So this will be ixx. The way izz is sigma m r square, where r is the distance from the z-axis. Similarly, since x is the distance from the x-axis, sigma mx square will give me ixx. And this will be izz. And this equation is the mathematical representation of the theorem of perpendicular axes. Before I wind up, one more reminder once again that the two axes need to be in the plane of the lamina and they should be intersecting the first axis, the perpendicular axis Z. Right? So with this we have looked at all the aspects of rotational motion. We have looked at all the concepts and theory associated with rotational motion. I'm sure you have got a very good idea about various concepts of rotational motion, and in the next couple of videos what I will do is we'll look at a few numericals on rotational motion and solve them to help us understand the concepts of rotational motion much better. Thank you.